Data race bugs are harmful, as we have seen, but the problem is that even though we want to detect them and fix them, data race bugs are notoriously difficult to detect. Even it is hard to detect than the deadlock bugs. Deadlock bugs are also hard to detect because their appearance or occurrence of the deadlock bugs depends on the thread schedule, non-deterministic thread schedule. But for the deadlock bugs, even though the occurrence is rare and not controllable, but once deadlock error occurs, then we can recognize them easily because it hangs the program. And although the hang itself is not visible, we have learned that there is a technique that precisely detect when the deadlock happens, right? By constructing the lock graph. So relatively easy to detect the deadlock because it is noticeable to the user. However, what about the symptom of the data race? Data race, the error of the data race is invalid update of the global variable. And such invalid updates are often very slight, and it changes some of the global variable's value into a wrong number, and it doesn't crash immediately when race condition happens. But the program survived for a long time with this wrong value on a certain shared variable that is slightly influenced to the other shared variable at some and we call such influences as error propagation. So error propagation happens, and at some point program crashes. But when program crashes, it is really non-trivial why the crash happens, because data race often has a very long path of error propagations. And what's more difficult is that data race, their occurrence does not always happen, but they happen only under specific thread schedules. And that thread scheduling case might be a very subtle ones, so that it can be easily missed in testing period. And even though the developer carefully program the multi-threaded program, since there are too many shared variables that are actually used in practice, so data can be easily missed. So people have invented automated technique that monitor the program executions and detect the deadlock, detect the data race as we detect the deadlock based on the observation on execution trace. And people have devised several techniques, and those techniques can be classified into two categories. And today we're gonna study the second category, what I call here lockset algorithm. And this is a very powerful and intuitive algorithm. So in this lecture, I'm giving you an idea of this lockset algorithm for finding data race bugs. So here, the key idea behind the lockset-based data race detection algorithm is assumption on lock discipline. Lock discipline means that when a developer or programmer writes a multi-threaded program, the programmer have this assumption in. The assumption is that every access to a shared variable must be guarded by at least one lock consistently, which means that for every shared variable, there should be one lock variable that actually guard the access to the shared variable. There always a guard lock for every shared variable. That is a kind of a way or protocol, or here it is called as a discipline, that ordinary multi-threaded programmers have when they write a code. And the technique called erasure monitor the program execution and to check whether this lock discipline is properly exercised across all part of the program execution. So what it checks is that every shared memory location, every shared variable, actually follows the lock discipline. And if it doesn't follow the lock discipline, it violates it reports such a case as a violation of the lock discipline, and violation of the lock discipline is too risky so that it is a bug. But the problem is that in C programs, it is not only limited to C program, but it is a more severe in C program, that it is a very non-trivial to know which log is actually designed to guard which shared variable. There is no information from the source code on this rule. Maybe that is in mind of the developer, but it is not written in the program explicitly. Then how can we check whether lock discipline is properly exercised? That is not easy. Maybe we can receive such an information to say that, okay, there is some list, and what is the lock that actually protect this list? And we can ask to the developer, and developer might say that, okay, M list is the mutex that actually guard access to the list. So whenever we read or write on the list, we need to first hold M list. Maybe that is the design of the programmer, but to the computer, it is unknown. To the computer, it is unknown. Maybe we can ask designer, the programmers, to explicitly encode this lock discipline in some form of the formal requirement. However, that is not easy to obtain in general. So erasure, what erasure does is inferring. What erasure does is inferring this lock discipline and try to check that whether, here we do not know which log is the one that actually guard the shared variable, but what erasure check is that no matter which log is, at least one log must be there for every read or write on a shared variable. And in opposite, if there is no log that consistently protect the access to the shared variable, the shared variable is in the risk, right? So we report such a variable as a kind of the cause of the risk of data race. That is the very idea of this tool erasure or algorithm erasure. So let me give more details of this algorithm of an erasure. And erasure algorithm, this is erasure algorithm, but erasure algorithm is also called as a lockset algorithm. So what erasure does is that erasure actually monitor every read operation and write operations on a shared variable. We can think on a shared variable. How that possible? We have technology for that. First technology is that for given binary code is a chunk of instructions, right? And per instruction, we can add some kind of a monitoring instruction so that to identify which thread is reading or which thread is writing on which variable. We can do that. Or we can run the program on a virtual machine, and underneath the virtual machine, we can monitor which variable memory addresses are accessed by which program in which thread in which program. Then we can extract exactly which thread is reading or writing on which memory location. That is something that we can obtain. In addition with that, the erasure also monitor all the locking and unlocking behavior of a thread in an execution. So erasure basically log them all. And what erasure does is that after logging on all part of the execution, and erasure look back this log to analyze, to find out some clue of a bug from the log in this way. So erasure, as it reads from the start, from the logging of the program, what erasure does is that for each variable v, or here variable can be written as a memory location. For each memory location v, erasure maintains a lock set. Lock set, it is represented as a CV. And C here means that candidate locks for the lock discipline. we do not know here exactly which lock is actually guarding the V, designed to guard the V. So what eraser first does is that for every read and write on memory location V, it actually maintains the candidate locks for the lock set. How that candidate locks are obtained. So meanwhile, what also eraser maintains is LT. AT is the set of locks held by thread at a moment. Thread T at a moment. That is LT. And so for each V, and for each V, eraser initialize the CV into set of the all locks initially. And for each read and write operation on V by a thread T, what eraser does is update the CV as a intersection of the CV at the moment and LT. And LT tells us that all the locks that are held at a moment when V is accessed. And here, if lock discipline is properly exercised, one of the lock in a LT is actually the guard lock for the V. And here we do not know them. But such a lock should be always appear when V was updated. So we can here reduce the V CV, which is from the old set of the lock, and per access we make an intersection out of them, so that we here reduce the possibility and try to find out the lock that is always held for every access on a V. But in this computation, if CV sub at some point becomes empty, then it means that for V there is no consistent lock that protect the V. So that eraser raise alarm that there can be a data race for V. That is how this eraser algorithm works. So let me give an example by using the previous example of the count. So here, let's check. So here, so originally the example was in Java. So here, the lock name is this, but you can simply regard this can be a M or X or anything kind of thing, anything other than this. Okay. So here we have one global variable balance, and balance here is intended to be guarded by lock this, but you here see that here at this moment balance is properly guarded by lock this, and its balance is properly guarded by lock this, but we have access to the balance without having lock this, right? So let's check this example, this execution scenario. So here we have a deposit. First is deposit, and we have a withdrawal, and they are executed in this order. I think this execution itself will be alright. But let's see how eraser works. So along this program execution, so eraser record all the locking behavior of every thread, and also it also records all the global variable accesses, so that this log was obtained from one execution. And after this, upon this one, eraser do the analysis. So it goes in this way. Initially, eraser set the LT1 as a null, LT2 as a null, because thread number 1 and thread number 2, they do not have any lock initially. Okay, initially. And here, this is the first. Let me clear my ink on this note for it to see the animation easily. So here, this is the first execution. So eraser revisit all the instruction that has been recorded in the logging. So here, thread number 1 is locking this. So LT1 is updated as in this form. The set that has this as its element indicate that T1 at this moment is holding lock this, mutex this, and then it move on to accessing the valence in here. So here it checks what's the candidate lock for valence. And candidate lock for valence is initially all possible locks. So I here put some as a mean to represent all possibility as an asterisk. So asterisk is now intersection with the LT1, and LT1 is here what? This. So the result become this. And it tells that, okay, here valence is accessed, and at this moment, this log was held. So I think, so eraser say that I think this is a kind of a candidate log for global variable valence, and move on. Here you have another access to the valence, and at this moment, the same operation occurs again. C valence is also updated. So here, at this moment, we already had a C valence as a set that have a this alone, and it made another intersection with LT1, which is also set having this only. So it remains as the same value. And let's move on. Next step. Here we have an unlock. So we here update the LT1 as a null. And move on to the next instruction. Here it is. So here we have another access to what? Balance here. We have another access to the balance. Sorry for my thick pen here. We have another access to the balance. So here we update the C valence candidate set of the balance, and I think it's wrong. Yeah, sorry. Here I think the contents in here is wrong. Here, this is not asterisk. At this moment, C valence is what? C balance is what? Sorry for the typo. C valence at this moment is this. So this is intersect with the LT2, but LT2 at this moment is what? This is empty set. So it make a intersection with the set having this and empty set, so it becomes empty set again. So eraser raise an alarm and telling that balance used to be guarded by this, but this instruction witness that there is a case that balance is accessed without having any consistent locking, which tells us that balance is not properly synchronized in its access, and this is vulnerable to data race. So eraser raise an alarm in here. So we have checked basic idea of the lockset algorithm, but lockset algorithm as itself produces too many false alarm because it doesn't consider typical pattern of the multi-threaded programming in accessing the shared variable. So it has been improved to consider some common codes of the false alarms and have a mechanism to moderate them. So let me give a quick idea on that. Quickly, the idea of such improvements. First point of the improvement is considering the initialization of the shared variable. So a thread write on the data on a shared variable without locking before it make a variable visible to the other thread, which means that a shared variable initially is set up by certain thread, and at the moment of the initialization, it is exclusively held by the thread, so there is no need to have a synchronization on that. So initialization is such specific period. So at the moment when only one thread is accessing for first time for initializing the variable, the lockset algorithm needs to be turned off. That is one thing that is in mind. The second case is that some variable was many of the shared variable in multi-threaded programs are set up, initialized, and then afterward they are only read and never updated. Then they are kind of a constant kind of thing, and there are many shared variable that's defined it at once at initialization part, and then after that all thing happen is simply a reading on them. And for those read shared variable, the lock set algorithm should be turned off because they are free from data race. And third one is the case for reader-writer lock. And as we learned from the earlier lecture, for when a user uses a reader-writer locking mechanism, then multiple readers can read on the same shared variable without holding a lock, right? So that such a case should be considered. So reader-writer lock is kind of a special case. So let me add one more description on this lock set algorithm for considering the first two ideas. Lock set algorithm consider the first two cases in a very smart manner, and it's very interesting. The solution for the first and second case of the false alarm is putting state machine to every memory location. So for every memory location V, the eraser maintain CV, which is a candidate set of the V, in order to detect the data race case. In addition to this information, for every V, eraser also maintain state or stage of the variable. So here's the detail. So for every global variable V or memory location V, the initial state of the V is a virgin. Virgin here means that this is just started, and then now it will be initialized by some thread. It doesn't know which thread it will be, but every global variable starts with the virgin, and then certain thread T is writing on the virgin state of the variable, then the variable state becomes exclusive. So it is by some writing by a thread T. Then it says it goes to the state exclusive means that, oh, this is the period for the initialization, but that initialization is exclusive to certain thread T. And this T is can read and write on this variable for a while, and then the variables, the state is remained as exclusive because this is the initialization period. So virgin is a pre-initialization, and exclusive is the initialization period, and it is defined by exclusive accesses by a thread. And after this period, after for a while, another thread read on the same variable, then the variable states now transit to the shared it, which means that, okay, one thread has been read and write on the variable, and another thread come in and try to read on the variable, then it means that, okay, this variable V might be a shared it, but it's a read exclusive. In such a cases, if other thread, for example, T prime or T or another thread is also coming, but they are reading on, then it remains on the state when it says it's a shared it. So here the state shared it indicate that, okay, this variable is has been initialized, and now it is shared it across the different threads, but still it is what? It is regarded as a read only. So it is fine. Or from the exclusive states, there is another thread coming and writing on that, writing on the variable. Then it goes to the shared modified states. It means that now the variable is shared and also is updated by the multiple thread. Same manner. So here, exclusive to the shared it's a read-only mode, but if there's another thread that is coming and try to write on that, then it goes to the shared modified states. And this shared modified state is important because, let me clear the pens. So this is the period where lockset algorithm is actually effectively working to detect candidate locks and also report data race bug. So from the initial state version, at this moment, CV is initialized as all possible locks. And if one thread is writing on the variable for the first time, then it goes to exclusive states, and this is regarded as an initialization period. At this moment, of course, this variable is exclusively held by the initializing thread, so CV is not updated because, of course, this initializer thread does not hold any lock because it is pre-shared yet. It is not yet shared this variable, so there is no need to hold the lock. So for the same reason, now CV must not be updated. CV remains as all possible locks. And then afterward, if it goes to the shared states, then it still have a chance that this variable is read-only. So shared state here means read shared. So at this moment, CV is now updated by intersecting with the LT, the lock that currently held by the accessing thread. But even though CV becomes empty, erasure does not raise an alarm because it might be a read-only. If it is a read-only shared variable, there is no need to really report the data race case. So it is silent, but it updates the CV, and the lockset algorithm actually report the bugs. It updates the LV, and also if it updates the CV with the LT, and it also report when CV is empty, when it is shared and modified, because this is the state where the shared variable is actually shared across multiple thread, and here we have a reader thread and also concurrent writer thread. So at this moment, if CV becomes empty, then it is a clue, very strong evidence of the data race. So it raises alarm to the user. That is how erasure algorithm works. And there is a more technique that consider more information from the execution order by employing different technology to more precisely predict the data race situation. But let me skip over in here. And also, there are some false negative cases. So there can be data race case, but that is not regarded as a data race. So people have invented to extend the erasure to consider more situation. And also another improvement to the erasure is improving the performance, because erasure record too many information and track too many instruction in a target program, so that it hurt the performance of the target program dramatically for this monitoring. So people have invented a way to cut off those monitoring costs with the different technologies. So erasure has been improved as well. And one of the nice approach for improving erasure is sampling. So we don't need to monitor all the cases for all possible memory location, but we first select some memory location that is very suspected to have a data race and focus our effort on monitoring and checking the data race only for those highly suspicious memory locations. That is another improvement. So erasure algorithm has been invented in the late 90s, and it's still evolving. And this is one of powerful technique that we have against the data race bug, which is a serious threat in multi-threaded programming. And this is still rapidly growing research field. So many papers and many research work is still on, and many publication is actively released on detecting and analyzing data race bugs.